Okay, now that everyone is settled in, we'll start with the next talk. We have Archit here giving a talk on memory is the agent, architecting stateful reasoning. Can we have a round of applause for Archit? Thank you, everyone.
Hello. All right. Good morning, PyCon 2025. It's great to see all of you here. I'm Archit, and today we're talking about memory in AI systems. So here's the core idea I want you to take away. Memory is the agent, and if you change what the system remembers, you change what it does. You don't swap the model, you don't have to rewrite the tools, you just change the memory and like what it knows about the past, about you, and about the world, and suddenly the reasoning takes a completely different path. We'll see this live in a few minutes. This talk comes with a working demo, and at the end you'll have a QR code pointing to the open source memory layer on GitHub, so you can explore it yourself. And also, I'll also talk about the production challenges that only show up when real users and real traffic hit your system. A quick intro before we jump in. I'm Archit, and I recently joined as a senior backend engineer at Abnormal AI. We build attack detection systems that processes over a billion emails every single day. I am passionate about distributed systems, large-scale infrastructure, search layers, and most recently, now, memory layers for AI systems. Let's take a quick look at how things evolved from basic chatbots to real intelligence agents. Uh, we'll rewind for, even just a couple of years back. Most AI systems were stateless, right? You gave them a prompt and they just gave you a response, and that was pretty much it. There was no memory, there was no context, and that was great for one-shot answers like answering trivia or asking for boilerplate code, right? But then came the next big step, which we moved on to agents, basically wrapping these models inside an agent loop recently changed the game. Suddenly, it wasn't just generating text. Now it could take actions like call APIs, run database queries, trigger workflows. Then it could observe the results, what came back, what failed, or what worked. And it could then decide the next step instead of waiting for a human to tell it what to do next. So that was the moment systems stopped feeling like just passive chatbots and started behaving more like autonomous problem solvers, right? So the kind you can give a task and not just a prompt. So then came memory, right? And this was a breakthrough because with memory, the flow changes, right? The agent pulls in past conversations now, goals, system events, even mistakes, and reasons over that history before planning the next step. So new observations feed back in. So tomorrow's reasoning is informed by everything that came before. This could be a simple key value store or a full-blown vector database with Postgres, just searching its own history semantically. With this, you do get a kind of a stateful teammate, one that remembers the bug that you hit last Friday, and the goal that you set on Monday, and the fix that you tried on Wednesday, and uses all of that to decide what to do next. Okay, we'll make this real. So far, we've talked about memory as an idea, but I want you to see this in action. So here's a simple journaling bot that I built just for demoing. At the start, it behaves like any other chatbot, right? You ask something, it responds, and the moment you close the window or start a new thread, it forgets everything. So we'll give it memory, and the same chatbot will become a learning, evolving agent with the same model, with the same tools, but now its behavior changes completely. So on the left, it looks like any normal chat. But on the right, that is where things get a little fun. These are the memory buckets. The first one is identity, which is who you are, your name, your role, and where you're working from. Principles are the rules that you follow. Focus are your current goal or deadline. And signals are patterns that it starts to notice over time. So every message you send can update one of these buckets, and every update changes how the agent behaves in the future. And once you build this out, three practical superpowers start to emerge, which is continuity, teachability, and learning. So those are what we are going to unpack next. We'll zoom in on what actually changes when you give these agents memory, right? And the first one matters the most when you are building real systems, which is continuity. Um, this is where chatbots start feeling intelligent. The first step of starting feeling intelligent, which is where you don't have to. There's no more re-explaining context now. The agent automatically respects the rules you already taught it, and your half-finished work becomes its starting point rather than yours. So we'll flip one switch so you can see exactly how much behavior changes the moment memory turns on. So here's a demo. Yeah, so memory is off here, right, at the right panel. So everything's grayed out. Nothing updates as such, right? So I tell the bot CI pipeline failed again. The bot responds with generic sympathy. It is okay advice, but notice what's missing there. It doesn't realize that this has been a recurring pain, right? So after the next message, it is still generic. It has no idea about the PyCon deadline, or there's no sense of history involved here. There's no notion of what past even means for the project. Because memory off, it's memory off, the agent can't carry the goals or progress forward, right? Because we've deliberately cut off its memory. All right, we'll see memory on now. Yeah, so user says, my goal this week is to stabilize CI before the PyCon submission deadline. Immediately you see the memories being created for main goal and deadline pressure, right? Stabilize CI before PyCon, and then from this point, when the memories are created, the focus card locks that in, right? Main goal, which is stabilize CI before PyCon. Deadline pressure, which is this week. From this point, the bot isn't guessing anymore. The only thing that is changed is that now we are reading and writing memory at each user turn. So the bot connects the dots. If you notice here, the reply at the last reply, it says great, CI is green before PyCon, right? So it's not random cheer anymore like last time. It knows the goal, the timeline, the next logical step. So that's what continuity feels like when a system actually remembers. So we held everything else constant, right? Same LLM, same tools, same prompts. The only variable that we changed was memory. So if you toggle it off, you get amnesia. Toggle it on, you get a partner. And that's continuity. All right, so here's what shipping this taught me pretty quickly. First is retrieval has to be fast. Why? Because every user turn already has a latency budget. The LLM and tools already take most of it. So memory only gets a small slice, and it has to be fast. So a good rule of thumb is to have P50 around 150 millisecond and P95 around 400 millisecond, even when fetching the top 10 memories. That is thanks to a hybrid index where we use semantic similarity and recency, decay, and priority, which we'll talk about in the next slides. Also with a tiny cache, so the hot memories come back near instantly. Secondly, always fail gracefully. Memory is a feature. It should not be a single point of failure, right? If the store gets slow or flaky, we should bail out right after 300 millisecond or any threshold that you want, and fall back to stateless mode. So the bot keeps working, then the user doesn't see an error spinner there. We just lose continuity for that turn. We can log the miss and move ahead and then backfill it later. So the third one is remember only what matters and not the whole messy chat history, right? Just the atomic bits, like in this case, we talked about identity, principles, goals, constraints, and signals, right? So we cap how many items per bucket we can store. We deduplicate it, deduplicate the near duplicates and decay the old stuff, and pin certain critical rules like use Flask for microservices in my project, right? So that's, you have to prioritize that on top. That keeps latency generally predictable and the agent aligned instead of drifting into random hallucination based paths. All right, we'll go concrete. We'll quickly go through this. We've been talking about speed. We've talking about graceful failure, and also keeping memory lean. This is the basic unit of memory in our system. We call it a memory item. Each one is atomic. That means one memory equals to one small fact the agent can use. So this is easy to score and easy to expire, and there's no giant black box state. So, I mean, the first thing is type, which is principle here. Principle saying never deploy on Fridays, right? Because we've all been burned by 9 p.m. rollbacks before. So the type is basically the category, and then you can have some predefined types. Then you have source and timestamp. We log who created it, the user, the system, or some external tool, and when it happened as well. So the timestamps let us decay these older memories automatically, and the fresh memories stay top of mind, and stale memories fades unless reinforced. So next one is priority. Priority is key here. Not everything deserves to stick forever. Critical goals get a higher score, so they resist eviction, and random throwaway comments from the user gets a lower score, so which makes it easy to forget. And finally, time to live, which is TTL. This one expires after 60 days, unless refreshed, as in unless retrieved. That way, we avoid infinite memory kind of bloat, and the agent doesn't start hallucinating ghosts from 2023 or something. I mean, 2 years back. So with just this schema, category, source, timestamp, priority, TTL, we can build memory that's small, explainable, and self-cleaning. So there's no mystery states, there's no hidden rules. Every fact the agent knows is right here, inspectable. All right, so now that we can store memories, how do we decide which ones matter right now? Because when the model is about to answer, we can't just dump everything it knows back into context, right? The latency will explode, and the prompts will get huge, bloated, and you will end up with a lot of irrelevant stuff, drowning out the main signal that you're trying to communicate. So, three factors here. Semantic relevance is vector similarity with the current query. So does this memory actually match what we're asking about? The second one, recency decay. Newer memories get a slight boost. Older ones just fade unless reinforced or retrieved. Priority is some memories are pinned, like principles I mentioned before, never deploy on Fridays. Should always stick around. So we weigh them so that the relevance dominates, which is 60% here. Recency gets 25% and priority gets 15%. You can tweak those numbers. A good rule of thumb is to just run experiments on your use case, because based on the use case, these numbers would change, and there could be more parameters that you could add here. And once we have the score, we only return the top 10 memories, and that keeps, again, latency low, avoids the huge prompt, and ensures the model only sees what actually matters. All right, so this is where things feel connected to RAG and search engineering, right, inside a chatbot, because you are basically building a little retrieval pipeline with ranking, decay, and priority baked in. And that is continuity. Of course, there's a catch here. Remembering is good until it remembers the wrong thing, right? So the next superpower we need is the ability to correct it. So continuity was all about remembering, that was one. But what if it remembers the wrong thing, right? Teachability gives you that. So continuity says keep the history. Teachability says, and if you got it wrong, let me fix it right now, right? There's no involvement of retraining here. There's no redeploying the system again. We just edit the memory entry. So the next reasoning loop, the agent reads the updated fact and changes its behavior instantly, right? So again, continuity gave us history. Teachability gives us control. All right, here's this journaling bot again. I tell it, coffee from Blue Tokai keeps me alive during late night deploys, right? Yeah, now we edited the memory slot there. We said Chayo's green tea. powers it deploys. Now you'll notice what happens. So when we edited the memory slot to Chayo's green tea, the next time the bot talks about deploys, the story kind of flipped there, right? Now it says Chayo's green tea powers the deploys. Why? Because the reasoning loop always reads the latest memory, right? Latest memory state before planning the next step. So one small edit here gives you a new memory, which gives you a different plan altogether. So this is how you can steer an agent kind of mid-flight, and if you change that memory, you change that behavior instantly. Um, the ability to shape its future behavior without restarting the whole system is kind of the takeaway for teachability. All right, we just saw how editing memory steers the agent instantly, right? So, but the moment you hand people this, feature, the users, someone's going to take a wrong turn for sure. And maybe they try a bold edit, or maybe they push something half-baked into memory. So the question becomes, how do you feel fast without living in fear of breaking things, right? So that's where versioning saves us. We never overwrite memory. It's append only and always versioned. So every edit just creates a new version, right? So in the previous example, when we saw blue Tokai being used, that's version 1. And when we switch to Chayo's green tea, that's version 2, right? So the older versions stay intact and nothing ever gets deleted, right? And if something does blow up, rollback is as simple as just read version -1, right? So you're instantly back to the previous state, and there's no migrations or no surgery, data surgery required on production. You just switch the reader, the retriever, right? So that's the safety net. Append-only history means you can move fast, experiment freely, and undo mistakes instantly. And that is teachability. All right, so we've seen continuity, carrying context forward. We've seen teachability, fix mistakes mid-flight. Now comes the final superpower, which is learning. Learning is what turns the system from reactive to evolving, because now it reasons over growing history and not a blank slate. So that's how we move from just one-shot chatbots to systems that actually learn over time and evolve over time. We'll take a real sequence here from our own runs. So day 1, the user says async is painful, right? That becomes a symptom in memory, which is async pain. So day 2, you try async io.gather. We log that as a skill learned, and now the system knows that you have picked it up, right? Day 3, you fix the Kafka consumer, and that goes in as a resolution. Basically, a problem solved, and this timestamp recorded, right? At the same time, your goal, which is stabilize CI before PyCon, gets stored. Not just the events, but also the intent driving them. So even your principle, no Friday deploys, becomes a rule. Even your little just chat, which was coffee, keeps me alive, lands as a trait in identity, right? So this is how casual conversations solidify into structured, retrievable memories. And the next time the agent plans, it doesn't see random diary entries and chat logs, right? It sees symptoms, skills, resolutions, goals, rules, and traits. So it becomes a knowledge base rather than just a diary, right? With a list of entries, just list of facts. All right, we'll see this as in action. I start chatting with the bot. Hey, I'm Archit. I'm based in Bangalore. We'll see location equal to Bangalore and name Archit. I usually spend weekends at Kormangla. Okay. Now that becomes a principle, which is a weekend routine. Later I mentioned Saturday was hectic, and that lands as a signal, right? That the weekend observation is hectic Saturday. So bit by bit, the bot isn't just responding, without continuity. It's building a personal kind of evolving memory of me. The identity, the principles, the focus, and the signals, all captured as structured facts, right? So the next time I talk to this chatbot, the agent isn't starting cold, like without memory. It brings the context forward automatically. All right, so here's the big picture of what we're talking about. Conversations build memories, which enable learning, which result in evolution, right? So with memory, agents grow because they can look back, connect the dots, and change behavior over time. And if there's no stored memory, there's no growth. It's that simple. All right. So remembering everything is still simple. Spotting patterns is where the system starts to evolve, right? So this little function says, if the same signal repeats enough times, let's say 3 times in a month, we promote it from a signal to a principal, right? So kb.count checks how many times this fact showed up. If it crosses the threshold, we write new version in the memory saying type equals to principal and value equals to promoted, and we tie it back to the older memories, right? We tag all the older signals as consolidated so that they don't clutter up future context windows. So the end results is like the casual events like weekend was hectic, right? Becomes long-term stable facts. It becomes weekends are usually hectic for this user because now the agent has seen, because of memory, that weekends are repeatedly hectic for this user, right? So weekends are usually hectic for this user. So that's how memory, again, stops being a list of facts or a list of diary entries and just starts being a more knowledgeable kind of assistant, a knowledge base. So now we have the full set. Continuity remembers across time. Teachability, you can steer and correct it. Conversations, learning, which is conversation solidifying into knowledge, so the agent evolves. With these three combined, memory isn't now just a feature. It's again the difference between a static tool that we saw earlier and a truly intelligent agent. Okay, let's quickly zoom out. We have covered the 3 superpowers of memory. We've seen how editing memory changes reasoning and how the same model with the same tools can take completely different paths depending on what it remembers. So what do we take away from all this? We have 3 big ideas here. The first one's the simplest. We've already seen this before, but it flips our mental model completely and how we look at memory. Memory is the agent. The memory don't just influence behavior, they define it. And if you change what the agent remembers, you can change the agent itself. And that leads to the second takeaway. If you want to steer the agent, don't fight the reasoning directly. You edit the memory instead. And that single shift from controlling outputs to shaping memories is what makes an agent teachable, correctable, and adaptable. This brings us to the design principle behind everything we've seen today. Don't start by obsessing over prompts or chaining tools or fine-tuning models. You start with the memory, and you start with the memory schema based on the use case that you have and based on what problem that you are trying to solve. Because once you architect memory well, reasoning naturally flows on top, right? If you get memory wrong, there's no amount of prompt magic that will save you. So the next time you are building an AI system, you remember this: memory is the agent. Edit the memory, and you edit the future. Thank you. You can contact me through LinkedIn. I'm fairly active through messages. If you find my talk interesting and if you want to discuss any concepts or ideas, or you can access my website. It has all my other social links there. So if you want other communication channels, as if LinkedIn wasn't enough. You can access the GitHub repo. The demo that we just saw, you can access this GitHub repo. It's a tiny memory layer built from scratch, just Python and Postgres. So it gives you a good enough thinking model around memory systems and how to enable intelligent AI agents. So yeah, I will skip the Q&A because I would like you to connect with me on the floor or on lunch, during lunch, and we can discuss anything further. Thank you.